time of our life here. Let's see. So I want to make sure, yeah, okay, so I'm going to skip over lots of slides. You'll see some X's. But to start with, first, what is consciousness? So we all know what you see, what you hear, what you feel, what you dream. Dreams are conscious. Dreamless sleep is not. So a little bit about myself. When I was 8 years, first of all of you started off really bright. I started off really stupid. It's unfortunate, but it's okay. I can prove it because when I was 8 years old, my second grade teacher told my mother, he might be able to get through high school, but don't expect he can get to college. And people now think, oh, what a stupid teacher. No, she was right. She was absolutely right, and I did want to get smarter. So I asked my dad what I could do to get smarter, and he told me, you know, if I understood what's in my head, I could be smart. And I thought, what a great idea. And that has actually been my motivation through my life. So I remember when I was 10 years old trying to figure out what's in my head, and I tried introspection, and you know, that doesn't work. It seemed to me that there was this homunculus, this little person inside my head looking out through my eyes, and that's silly, and in particular, it wouldn't help me to get smarter, which is what my goal was. Anyway, I did manage to get to college. I got to MIT. I was very, very lucky with that. And then, I mean, I've been very lucky in many ways. When I was 18 years old, I was a junior at MIT. I apprenticed myself to Dr. Warren S. McCulloch, the same McCulloch and Pitts, who actually defined the formal neuron. So you see here a little picture of the kinds of formal neurons he had. Jerry Letvin told me that this is the only kind of place in the world where the arrows point in the wrong direction. Anyway, you know. Anyway, those are the. Let's keep on going. So the Turing machine versus the conscious Turing machine. The Turing machine is defined to understand computation. The conscious Turing machine is designed to understand consciousness. It's based on Turing's machine and Barr's theater model. The CTM is not a Turing machine. So I want to describe to you what this model is. So you understand, we are not modeling the brain. We are trying to understand consciousness, and we think we can understand it without modeling the brain. I think the model that you'll see is as good for the octopus as it is for the human being. Okay, so it's based on the Turing machine. I assume you know what the Turing machine is. Barr's global workspace metaphor. Barr's describes what's in one's head as a huge auditorium with 1 million processors looking at what's going on the stage. And what you're conscious of is just what's being seen on the stage. All these processors doing stuff, you have no idea what they're doing, only at some point they somehow get together and manage to decide what should happen on the stage, how that play should proceed. And so the processors decide how the play should proceed, and that's how it goes. Barr's does not say anything about how these processors decide. He has a central executive which helps them do it. What we wanted was a model of what's going on that's like that, but that's as well defined as a Turing machine. Completely well-defined model. So here you see the auditorium. This is much less interesting than Barr's. It's just one person up on the stage, like a radio show speaker, and what the speaker broadcasts is what the CTM is conscious of. That's it, nothing else, just what that speaker broadcasts. So the processors compete in the tournament. We are very precise about this, the tournament, to decide which processor's idea will get broadcast. So there you see bars on the left, nice, interesting play, Blum on the right, just a speaker. So from now on, global workspace, which was Barr's wonderful invention, refers to Blum's version. Okay, so about the global workspace, the CTM is not conscious of the world directly. I'm thinking of you as being conscious Turing machines. That in your head you have a conscious Turing machine, so I'll be, anyway, so the CTM, which would be you, is not conscious of the world directly. The inputs from the world go to, eyes, ears. Those eyes, ears, sensations have to convert right there at the input, convert that input into something we call a chunk of information, a short string of information. And that chunk of information is all that you are conscious of. And this helps to explain how it is you're able to dream. Because at night, of course, that the dream is being created entirely in your brain, and it just seems so impossible for that dream to have all of these bits. It doesn't have all of these bits. What it has is a short piece of information which is either something it's seen before or something related to it. The machine has a lot of prediction going on, so it has the machinery to change what it's seeing. Every time the machine looks out in the world, it has to predict what it will see, and of course, what it will see will be a little different, and so that little difference will be used to make that prediction machinery work better. So the CTM is not conscious of the world directly. Input processors convert inputs to these short descriptions that we call chunks, and the CTM is conscious only of those short descriptions, those chunks. But how are those short descriptions created? The CTM is born without any language, no language. It will create the language for itself. So the CTM will learn English, say, and be able to talk to you in English, but internally it is creating its own language. This is a multimodal language. You can get the idea when you have a dream, that frame is a chunk of this in this language. Okay, so Brainish is the multimodal language used by processors for interprocessor communication. A conscious thought, whatever that thought is that's in your mind, that conscious thought is a broadcasted Brainish chunk. Right. The frame of a dream is a broadcasted Brainish chunk, a hope, a concern, a pain. These are all Brainish chunks. So I'm going to cross out, I've crossed out a bunch of slides because I want to end. Of course, I want to say what relevance this has. As you can see already, I'm a mathematician, a computer scientist, a theoretical computer scientist. It's as is Lenore, and so what you're getting from me is just theory, right? But we're very happy with this theory because you see, let me just mention that since I was a kid, I wanted to understand what's in my head. And yeah, so what am I saying? So I lost track. What? Yeah, I want to understand what's in my head, but I lost track. Okay, so this thing had to do with the fact that there This auditorium has 4 types of processors. Input processors. The eyes themselves convert what is seen into a chunk. It converts what you hear into a chunk. What you feel, what you was touching, it's converted into a chunk. It's those chunks that are then sent on to consciousness. Okay, so there are these 4 types of processors. Okay, oh, good, okay. So let me give you an example of how this works with the birth of an infant with a CTM brain. So I go to the infant because, you see, you don't yet know how this thing is working, and it's kind of nice the infant doesn't either. The infant is born, it has no language, the processors are not connected in any way. For one processor to talk to another, it has to get up to its information up to the stage, broadcast, and maybe another processor will answer. You know, when you're in a party and you don't know the person's name, oh, damn, I forgot her. What's that name? That processor is very embarrassed, gets up on the stage and says, I'm embarrassed, what's her name? And you know, maybe, hopefully, some processor in the audience, you don't know where that name is, hopefully some processor in the audience will come up and give you the name. Isn't it interesting that it often comes up like when you're driving home? An hour later, the name comes up. What the hell's going on there? Well, it tells you something. Some processor has still been looking for that name, and it finally found it, and boom, it gives it to you, but you're driving home, it doesn't do you any good. Okay, so an example, the birth of an infant with a CTM brain. So the infant is born. I'm going to assume that this is a very nice, easy birth. Births are not necessarily nice and easy, but the infant is born. I'm assuming also, of course, that infant has a CTM brain. So let's see how this thing works with that infant. So in fact, the infant actually has good eyes. But you know, the infant has never seen anything, and all it's conscious of is a blob. That's it, only a blob. But this machinery that does prediction, observes, corrects the machinery, this machinery is working all the time in those input processors, those very input processors that are creating the chunks. So the blob becomes clearer with time. Okay, so let me try to show you what's going on with the birth of an infant with a CTM brain. So the infant is born. So when it's born, so you have all these processors, and these processors are creating chunks. Each chunk has in it maybe some description of what some idea that it wants to get broadcast, and it assigns it a weight. Maybe positive, something you want to have, negative, something you don't want to have, but a weight to indicate how important that chunk is, how important that idea is. So here, the first few broadcasts are actually trivial. The infant has just been born. All the processors are perfectly okay, no problem. And so the first chunk that's produced is this P1, a processor, that's a processor name, the time it got produced, a nil, which is going to end up being the information, but there's no language, so nil and 0. All the chunks, all the processors have these chunks with essentially no information, and they compete in a tournament to decide which one gets up to the top. In this particular case, every processor's idea is equally likely to get up to the top and be broadcast, and it will not have any information. But you know, the infant's just been born, and the time comes when the processor that measures oxygen says, I need oxygen. So for the first time, there's a chunk that's produced that's different from the others. It's a particular processor. Here it's P sub x, which at this time is still producing no information. It's just a nil, but with a negative weight, -1, and then -2. I need oxygen. I need oxygen. I need oxygen. It gets loud. Eventually, the complaint is loud enough to force every processor to do whatever it can to counter the pain. This is built into all processors. If you see something negative, you must do what you can to counter it. And when it gets less than this theta, less than this particular threshold, at some point it's even so much less that it must even stop the things that's necessary, like breathing. I don't know if you've had that experience. If it's really, really important, you even stop breathing. This thing stops breathing, and the processor is told, you stop breathing, you can only live for 3 minutes. So only in that case do the processor stop everything else. Okay, so the first few broadcasts are trivial until at time t, a gauge processor that measures oxygen starts to complain, and here you're seeing the complaints. Eventually, the complaint is loud enough to force every processor to do whatever it can to counter the pain. At that point, every processor does whatever it can. This is an infant that's just been born. It has no idea what it can do, no idea. So the processor that controls the legs will start to flail the legs. The one that controls the arms will flail the arms. The processor that controls the pees and poos, they're doing whatever they can. And at some point, the infant screams and cries. And those cries bring in the oxygen. Wow, that works. So, in fact, that gives rise to the first significant word that the CTM will produce. It's the brainish word for pain. So what's happening is that this particular processor that needs oxygen at a certain time still has no language, so it's nil, but a very negative weight. And that particular chunk is what pain is. From now on, whenever any thought that goes back to that would be the word would be the short pair PT, the processor that created the chunk, the time it got created, and that would be the word, and it would point to this chunk which has more information. In this case, the additional information is just this very negative weight. So the infant's first significant word will be this word. Consider it the brainish word for pain. The definition for it is this word together with nil, no information at all, and a very negative weight. Of all the things the infant did to stem the pain, it's the crying that countered the pain, and the infant's second most significant word will be, here it's PYTY, that the word for cry, it'll be the word for cry. Crying is good. When something is negative, when things are bad, cry. Scream and cry, yes.
In this model, how is it clear that it was crying that countered the pain and not a delayed effect of flailing the arms?
All of these things happen, but each thought is an individual broadcast. So one of them is, whatever is flailing the arms, there's a thought that goes up there so that has to do with those arms. It's arms, legs, being food. At some point, it's the screaming and crying, and then until that happens, the pain is getting worse and worse and worse, and then the crying happens, and now the pain starts to subside. That's how it knows.
So is the
Good
process
question.
of trying different things random here?
Sorry, you have to speak much louder.
Is the process of trying different things random? Like flailing the arms, pooing, stuff like that?
It's random. Whenever there's so I haven't talked about how it's decided what gets up there.
No, but if it's random, the degrees of freedom of a baby, baby are so high, then the chances it will find crying before it dies seems actually pretty small. So I'm asking if
That's
it's
good.
something-
This saying that it's not that small. It turns out that these chunks, if they have no information and their weight is zero, they're all equally likely to get up there. There's a probability associated with this. But in fact, by this time, there are a few things happening. And because their weight, because you know about them because their weights were different from zero, and now among them different ones are chosen. You don't look too happy. You think that it's much more than that.
No, it's much more than that. I'm just saying that there is a very large search space here.
Yeah,
That's
million
the
processors.
Search.
A million processors.
But the crying is the only thing that makes the oxygen gauge.
Yeah, he understands that. He wants to know, well, of all the million things that could be done, how come that comes up? And the point is that really the only processor, they're all trying to do something, but the only processors that are effective at all are the processors that actually affect the actuators. So what's clearly getting up in the case of a kid, that's the arms flailing, the legs, much less, yes.
The stage is just what you're conscious of. These things are all happening in parallel. So this
These-
is not talking
yes.
about, it's not a sequential process of of whatever gets up there is what you do. They're all being done. So I think this doesn't speak to what actions you do. This only speaks to what you're conscious of.
Yeah, okay, that's very
Right?
good.
Because these are all happening in parallel. and it
You're
doesn't say
absolutely
about
right. I didn't say that.
the
I didn't
strategy for doing
even realize that. Thank you. Yes, they are all happening, and the arms failing, well, that will get up there, and then it'll become conscious. Okay, thank you. Yes.
Do all mammals start breathing by some sort of crying first? Non-humans.
I don't know anything about deer or dogs or. Sorry, I just don't know.
I guess you would say that they.
I'm hoping that this will work for octopuses also. So, in fact, an octopus is probably a processor for each arm. Megapus would have 1 million processors, one for each arm. Who knows what they're for? So anyway, the second most significant word is the word for cry. And in time, the infant will learn that whenever it has pain, crying works to counter it. So the first significant word is the word for pain. The second significant word is the word for self. Self is whatever you have power of thought over. I can move my arm. I have power of thought over this arm. That arm belongs to me. Your arm, I can't move it. I do not see it as self. So the baby will acquire the word for self. And I guess Lenore showed the baby early in life discovering its left leg. It has power of thought over the left leg. Oh, that's a wonderful thing to know, and that's labeled self. Okay, so this brainish dictionary that's created, it's a dictionary of all the broadcasted chunks. A word is PT, a gist, a short gist, and a weight. That's what the dictionary is about. The word PT will point to the chunk in the dictionary. It's very easy from PT to look up that particular chunk, the meaning of it, which is the full chunk. All processors have the same created dictionary because it's a dictionary of broadcasted chunks. It's their interprocessor brainish dictionary. Something gets up to the stage, it's broadcast, all the processors put that chunk into their dictionary. And so, this definition of the machine has no, let's see. So it's a 7-tuple. Lenore talked about that, but it doesn't matter. CTM has no links at birth. Time passes in ticks. Chunks are words of brainish. The tournament, this is this is an example of something of how it's decided which processor will get to the stage. The tournament, this is interesting, it's one of the theorems. Yes? 7, 5, 5. Got it. I won't go through this. This tournament is a tournament which for deciding which processor will get up there to, and it's a winner-take-all scenario. When two processors play, the winner gets all of the weight of the loser, and there is then a proof that each processor will win with probability proportional to its weight. And I have not seen that in the literature. I'm very proud of this one. And this is actually a proof working its way up to the fact that the probability of F winning, F having weight 9 out of 31, is 9 out of 31. This is a nice one too. We mentioned to Avram when we were doing this that we had a problem with weights. We didn't know quite how to set those weights. Actually, what we needed to know was how to keep the processors honest. And it was great. Avram said, Mom, Dad, I've got just what you want. Got a paper for you. Sleeping experts problem. It has to be adjusted to the model, but that seemed to work. Conscious attention. You know, recall my homunculus problem. Introspection suggested a homunculus. Conscious attention is when the chunk is broadcast, all the processors get that chunk, and they put it in that chunk in the dictionary. They're all seeing exactly the same information at the same time. Seems to not be, it's okay. So actually that solves the homunculus problem. They're all getting exactly the same information at exactly the same time. I wanted to talk about pain and pleasure. Oh yeah, pain and pleasure. I'm really interested in understanding pain. Lenore's really interested in understanding pleasure. This, we've divided up the work among us. I wanted to talk about phenomenal consciousness. I'm sure I'm getting down to very little. It's, it's been said that pain, the question is, how is it that you actually suffer from pain? We know how to build a machine so that it knows when something is damaged. Just some signals being sent. You know that there's something damaged. But how do you make that machine actually suffer? Suffering is very important, and that's a hard thing to understand. I was very lucky. I was thinking about that, wondering about it. The people have thought about it, say that it's an illusion. Oh, come on. Pain is an illusion? That's crazy. It's not an illusion. I feel pain. That's really... But then I took a nap, and that was a very nice nap. In the nap, I had a dream. And in that dream, I had a terrible cramp in my right leg. Terrible. And I woke up, and there was no cramp, no pain, nothing. I touched my leg. There was no sign that it had ever been cramped. That's when I realized, yes, that was an illusion. That terrible suffering was an illusion. And my body was proving to me that it could create the pain of a cramp. Okay, intense pain, less intense pain. How many, do I have a minute? 1 minute. We have 2 axioms of consciousness. Axiom 1 saying that, explaining why that homunculus appears to be, why all these processors can appear as one. Axiom 2 is explaining how you actually get the suffering from pain. I won't go into that. So I do want to distinguish the suffering of pain from the knowledge of pain. You've already seen one explanation? No, you didn't, but the processors cannot do anything but attend to the pain. when you have a very severe pain, you cannot do anything. So what does that mean? You can't do anything, therefore you feel pain? Or is it that you feel the pain and therefore you can't do anything? I really thought, okay, you can't do anything. The processors are built so that they cannot do anything when something is damaged, and therefore you feel pain. But actually, it could just as well be that you're right, that you feel the pain, and that's why you can't do anything. Most likely it's both. Here's another explanation for the suffering of pain. The suffering of pain comes about when the injury in the model of the world is labeled pain and self. You see yourself with a skinned knee, that's labeled, that's the illusion, that's labeled with the word pain and with the word self. And I haven't explained this. Pain and self are labels like colors in the model of the world. How can mere labels generate pain? Well, they're not mere labels. They are brainish labels. And just like a frame of a dream, when you have a dream, that's a brainish label. So they are created in a dream by the same prediction mechanism that does predict observe. Okay, here. So this is weird, right? I didn't believe that suffering could be explained as an illusion. But fortunately, there is an argument for it, and I'll give you that argument. There is a disorder called pain asymbolia. Not symbolia, asymbolia. Pain asymbolia. This is a very interesting disorder. If you have it, you know when you have pain, you can get cut, pressed, burned, whatever. You know about it. You know how terrible it is, how the weight of it, but you don't suffer. It's okay. Isn't that wonderful? Many people would like to have pain asymbolia, but I can tell you that kids that are born with it don't live more than 3 years. That's it. You really need to suffer in order to do something. So I'm coming close to the end now. In the disorder called pain asymbolia, the patient knows she has pain but does not suffer. The first explanation by Grayek said the patient is not conscious of the pain, but is conscious of the self. It's conscious of that label self, but not the label pain. And then more recently, Colin Klein says, no, the patient isn't conscious of self. It is conscious of the pain, but not conscious of self. Two different arguments. And then even later, Philip Jarens, that's just a couple years ago, asks, which of these two explanations is correct? Which one? And the nice thing about this is that and I didn't explain enough to you, but the nice thing is that the CTM model is saying both explanations are correct. There are some people that there are two pain asymbolias. There's the pain asymbolia when you're conscious of self, but not the pain, and the one where you're conscious of pain, but not the self. So about models of the world, this is my next to last slide. You want to? Okay, so it's almost done. I once thought that the model of the world is like a train set, or a collection of train sets. That wherever you go, there's this train set, which is a model of the world. The conscious Turing machine gives a very different idea of how that model of the world works. It's entirely described by a set of short phrases called chunks created by those input processors. When CTM wants to do something, to think about something, to accomplish something, it's a processor that gets up to the stage and asks. You don't know exactly. Can you wiggle your ears? Some people can, some can't. You have no idea until you try it, and then maybe you then touch your ears to see if you can do it. Some processor is asking, wiggle your ears, and if you have a processor that can do it, it gets done, otherwise not. So here's, for example, assume that my brain is a CTM and that I'm thirsty. The thought I need water is generated by a processor that gets up to the stage, which is what I'm conscious of. Then this causes, so that processor, I need water, get me water. Another one comes, processor gets you up from the chair and says, well, what next? And then the third processor actually walks you out to the water fountain. Anyway, that's, so the model of the world, the thing about the model of the world is all in those input processors. It's in those same algorithms that ChatGPT uses to give you such wonderful information. And that's a summary, and that's the end. Okay. Yes.
So going back to what you started with, when a baby is born,
Yes.
the baby is also born with some instincts. The baby knows what to do.
This is not a model of the baby. This is a model of consciousness,
So my
and it's a
question-
mathematical model. And in this model, yes, there are some things like instincts because
So how do instincts fit into this?
the processors themselves, for example, there's certain. I didn't say what's built into the processors. I said one thing: when the processor sees there's something very negative, it must try to do something to counter that negativity. Is that an instinct? That's an example. I haven't told you what's built into the processor. Not too much, but that's one important thing.
I was just curious. So if there's an animal that has only instincts, all of its behavior, everything is instinctual. In your model, will that still be conscious?
Yes. Good, wonderful question. Yes. If the CTM is a correct model, it will be conscious. There's nothing really about how brilliant it is. Yes.
If I were to build a CTM, would the building blocks of nuance and synapses be sufficient?
Yeah, so we have 1 million processors, but that's actually a variable number. You could choose different, but we have 1 million processors, and given the number of neurons in the brain, that's about 10,000 neurons per processor. I view the processors as being like laptops. Okay?
Let's do one last one maybe.
Yes. Go ahead.
Thank you so much for a great talk. I really think that bringing cognitive task, cognitive ability, and the word cognition into this CTM model would be much, it will be more effective and make it broader, and I think it will match mostly to the different levels of cognition we have and cognitive areas in the brain. Just instead of using the terms of processor and chunks, looking it into the different levels of cognition, this will help us to better formulate and understand consciousness in AI models, and also intelligence as a separate term that we use, but these are ambiguous. But with cognition, we can probably make it more.
Okay, so that's a very good point. We could have made the model more complicated to include stuff for cognition. We did not. We wanted a very, very simple model that would explain a lot. And we tried model after model after model, and in each case we found that in order to be able to explain more, we had to make it more complicated, and we threw away the model. And we finally came to the CTM. The CTM maybe doesn't explain, the CTM has a nice property that if you want to understand something via the CTM will give you at least some idea how to answer that question.
Okay. What? Last one.
Okay, I'm wondering how learning and updates to the dictionary take place. That can be formulated.
Thank you, that's very good. So every thought you have, 10 times a second, there's a thought. It's the alpha rhythm. 10 times a second, processors put a chunk into the competition, a chunk wins, it's broadcast. When it's received, that's what you're conscious of, and every processor gets that broadcast. every processor puts that chunk into its dictionary. So the chunk is being built up one at a time, one after 10 times, 10 new words per second.
But I guess at some point you would run out of space or capacity, so you just stop attending to
Processors.
certain parts of your dictionary?
So we do have a lifetime on the processors. The lifetime is chosen so that it's roughly 68 years. It's 10 ticks per second, and you can, and the number of processors you need. The lifetime is determined in part by the number of processors. You need always to have enough processors, and at the end of that time, the machine dies. So I'm past. I'm
All right, thank you very much, Manuel.
Thank you.
And let's meet back at 1:45.